So today we're going to start talking about conic sections. And then our second topic is going to be how do we use shifts and exponent properties to make it easier to graph some exponential functions that have more than just x for the exponent. Maybe they have 2x minus 7, or maybe they have 5 plus x, or something like that. How can we graph those a little bit more easily? So first, as we talk about conic sections, let's talk about what the 4 conic sections are and why they are called that. Does anybody know what I'm talking about when I say conic sections, or why they have that name? Anybody want to make a guess? When you see the word conic, what do you think we're going to be talking about in math class? Cones. And when we talk about sections, we're talking about cutting into some sort of pieces. So conic sections are the different kinds of shapes that you get when you take a cone and you take like a giant razor blade and cut through it. So the intersection of a plane and a cone. Except a real cone is more than what we normally think about. We normally think about one that has a base and then comes to a point. In reality, it doesn't have a base. It goes on forever and ever, and that's only half of the cone. There's one just like it, inverted, so that they touch tip to tip. So now let's start imagining some of the different shapes we might get if we take that giant razor blade and cut through it. So if I take a cone and cut through it, so imagine your ice cream cone, cut with a giant razor blade, what shape do you have around the top of that cone? A circle. A circle is one of the conic sections, and it is in fact the only one that we're going to talk about equations for today. We'll do these other 3 later on in the course. Can you imagine any other shapes you might get if you cut through the cone a little bit different way? So we've taken our cone, we've cut, and we've got a circle. What if we tilt this plane a little bit different way? Can you think of any other shapes that we might get? Abby? Well, we kind of think of a triangle, except remember that it goes forever and ever, so we're never going to get that bottom side of the triangle. Jack?
Would it be like a graduated cylinder or something?
That's a good guess, but we're not going to get that. We're going to take, we'd be doing other things to get that.
Ellipses?
An ellipse is one of the ones. Ellipsis is your ... Ellipse is the shape that we would get if we tilt it just a little bit. So instead of going perpendicular to the axis through the cone, we go at just a little bit of an angle, and then we get the ellipse. So instead of going straight across, I've tilted it a little bit. If I tilt it just a little bit more, I might not go through the other side of this circle. I might get my parabola. So I've tilted it just a little more. It's not going through the top part, but it does not cut through both parts. It goes forever, and we get the parabola. So do you kind of see where that one's coming from? And then the last one is if we tilt it up enough to go through both halves of the cone, I'll get sort of a parabola down here and another one upside down up here, but it isn't really shaped like a parabola. It is what we call a hyperbola. So do you kind of see how we can get those? And that's why they are called conic sections, the shapes we get when we cut through a cone. So since circles are the only one we're doing today, how many of you guys have at some point or another played with a math compass? So you put a pencil in and you've drawn circles. Everybody's pretty much. So we know the locus definition of a circle. We have that fixed point, and as long as it's not a super cheap compass like I've sometimes played with, where it comes more and more apart as I try to draw my circle and I get a spiral, as long as it really stays put, I am drawing everything. That distance stays fixed, so I stay a fixed distance away from the center. So our locus definition of the circle is all of the points that are equidistant from that fixed center point in the plane. And I've got to say in the plane so that I stay with 2D. We know if we do 3D, we get a sphere. So what that means is if I have a general point, xy, and then I have two numbers for the center. I don't know what they are, but I'll call them hk, but those are fixed numbers. If I want to take the distance from my general xy to that point, I'm going to do the square root of x minus the first coordinate of the fixed point plus y minus the second coordinate of that fixed point. And because I'm using my compass, I am always going to get the radius for that distance. So that says the distance from xy to the center is r. Now, for our standard form for a circle, we're going to square both sides of that, because when we're doing our equations, we really don't like ending up with these big old long square roots in them. So our standard form for the equation of a circle is to take x minus this coordinate of the center squared plus y minus the second coordinate of the center squared is the radius squared. So if these are both positives, we'll see the minus signs, but if one of these is negative, it'll always look like the opposite of the coordinate is what's inside the parentheses there. And that is going to be our standard form. And I am going to accept it either way. If your radius is 3, you can either say 3 squared or you can say 9 on that right-hand side. I'm not going to make a big deal about that. We know, though, that we could FOIL out each of those parentheses, and we'd get x squared plus something plus y squared plus something, and we could combine a bunch of like terms and all of that and get a general form. For any conic section, you can get a general form that is ax squared plus by squared plus cxy plus something times x plus something times y plus a constant equals 0. Now, if it is a circle, we will not have this in a circle. In other words, c would be 0 if it's a circle. In addition, if it's a circle, a and b will be equal. But we will be writing equations in standard form and in general form. General form, we need to know it's going to be this order. So we're going to have the x squares, then the y squares, then the x's, then the y's, then the constant equals 0. Is that much making sense to everybody? Okay, let's go ahead and try an example where we describe a circle and we try to come up with these equations for it. So I have a circle with radius 5 and the center is negative 2, 8, which you see there on the graph. This one does not specifically say we need to graph it, but you will have some in homework sets where you do. And here's what I'm going to expect when you are graphing a circle. We're going to plot the center, and then we're going to go and plot points in the 4 easy directions, straight up and down, straight left and right. So if I go from negative 2, 8, and I go straight up 5, I have negative 2, 13. And if I go straight down 5, I have negative 2, 3. If I go to the right 5, I have 3, 8. And if I go to the left 5, I have negative 7, 8. After we plotted those 4 points, we're going to do the best we can to connect them with a circle. And I would expect those 5 points to be labeled so that we know what we're talking about. So does that much make sense? Now, maybe not quite so much labeling if the radius is a weird number. If the radius is the square root of 7, we'll relax a little bit what we're looking for, but most of the time we're going to be dealing with integers for that much. So let's take a look at what this one does ask us to do. It asks us to get the general form of the equation, or the standard form and the general form. So first the standard form. Here is our formula. We're going to plug in the center for that. So we're going to say x minus negative 2 squared plus y minus 8 squared equals either 5 squared or 25. I'll take that either way. But do you see how it looks like the opposites of these are the coordinates of the center? And that is our standard form, and when we're asked for both, we need to make sure that we label which is which. This one also asks for the general form. So how do we get from that to the general form? What? I think I heard somebody say it. We need to FOIL it. So we're going to have x squared plus 4x plus 4 plus y squared minus 16y plus 64 minus 25 equals 0. And then I just have to combine terms and get things in the right order. I'm supposed to have the x squares, and then the y squares, and then the x's, and then the y's. And let's see, then I've got 68 minus 25. What will that give me? Plus or minus? Plus 43 equals 0. And that will be my general form. And for right now, that's all we're doing with circles. We'll keep building on that, but that's enough circles for the first day of that, unless you have questions. Okay, then moving on to the exponential forms, I want us to first do a quick review of our shifts, because I said we're going to use exponential properties and shifts to figure out what these graphs need to look like on the ones we're about to do. So if we move to the right, is that plus or minus inside or outside? What do we got, Elizabeth? So we're going to be subtracting inside. Left is going to be adding inside. What if I want to go up? Add outside. Down is subtract outside. If I reflect across the x-axis, I change y to minus y, or f of x to minus f of x. And if I reflect across the y-axis, I change x to minus x. So we're going to keep those in mind as we do things like this with weird exponents. So I'm going to teach you a trick on that. It's not exactly what the book does. We want to use our exponent properties to get the exponent to start with an x. And then we can use transformations. So we want to get to where the exponent is x or x plus something or x minus something. So I'm going to take y equals 2 to the, well, I wanted to start with x, so it's easy enough to use the commutative property and say that's minus x minus 2. Okay, so now it's starting with minus x, and I wanted to start with just 1x. So I can factor out a negative 1, right? So I could say that that is 2 to the negative 1 times x plus 2. And you probably are very quickly going to go straight from this to that. Now, next property that I want us to use. If I had, oh, I don't know, b to the n m, I know that's the same thing as b to the n times m, right? So I have 2 to the something times something. So I am going to say I could just take 2 to the first part of that, and then take that whole thing to that other power. Does that step make sense? Because that's the whole trick on this. Get this property out of the way. Don't we know what 2 to the minus 1 is? And we have just added 2 on the inside of the function y equals a half to the x. If I add on the inside, what do I need to do? I need to do what? No, if I add on the inside, with our transformations? What does that do to the graph? If I add on the inside, then I need to shift 2 to the left. So I need to take the graph of a half to the x and shift it 2 to the left. So I'm going to do dots for my graph of y equals a half to the x. So 0, 1, is that going to be exponential growth or decay? Decay, so -1, 2, -2, 4, -3, 8, and I'm going to have a horizontal asymptote along the x-axis. That's all I need to do for the graph that I'm going to shift. I'm not going to do it solid because it's not my final answer. Then I need to move each of these dots 2 to the left. So 0, 1 moves to the left and is now -2, 1. 1, 2 moves to the left, so it is now -3, 2. -2, 4 moves to the left, so it is now -4, 4. Did I get that right? -3, 8 moves to the left, so it is now -5, 8. Always check asymptotes. If my asymptote slides 2 to the left, does it look any different? No, it's still going to be the x-axis. So I have these 4 lattice points. And I'm going to check -6 would be off the grid, so I'm not going to plot any more that way. And then I also want the y-intercept, because that's always a critical point. So if x is 0, what is a half to the 0 plus 2? What's a half squared? 1/4. So this y-intercept is 0 1/4. So I want to see all lattice points labeled and y-intercepts. You may label them either on the graph or in an XY table. If you do an XY table for what I've done in blue to figure out some of those points, please just draw a single line through that when you're done so that I know that is not part of your final answer, so I don't get confused trying to grade things. Does that make sense to everybody? Okay, let's do a couple more. These will go faster now that we've done the first one, but these are new and different and kind of take some getting used to. So this one, you're probably going to have a pretty good idea from what we just did as far as what you need to do to that. You need to think of this one as f of x equals 1/3 to the -1. And what do I have left if I factor out the -1? X, what? -1. And then we are going to regroup. What is 1/3 to the -1? So we are graphing 3 to the x minus 1. Growth or decay? Shift which way? -1 on the inside goes which way? So we're going to do 3 to the x and shift it right 1. So if I do 3 to the x, I have 0, 1, 1, 3, 2, 9, and anything else is off the grid. And I have the x-axis as an asymptote. If I shift everything to the right, if the asymptote shifts right 1, does that change anything? So then I'm going to shift each of these to the right 1 and figure out their coordinates. So I have 1, 1, I have 2, 3, and I have 3, 8, right? No, 3, 9. Did I graph that one right before? 3, 4, 5, 6, 7, 8, 9, yeah. Does that look right for those points? My final graph is the only one that needs to be solid. And then I get my y-intercept. If x is 0, I have 1/3 to the first. So there's my y-intercept. Okay, slightly different trick with the very last one that we're going to do. graph g of x equals 2 to the 2x. Now the book talks about that as a transformation. Oh, we multiply x by 2, that is going to make it steeper, which it does, but it's kind of hard to figure out how much steeper the way that the book does it. So we're going to do the same trick that we just had and regroup so our exponent starts with x. Don't we know what 2 squared is? And do you guys know, and you better say yes, how to graph g of x equals 4 to the x? Exponential growth, nothing to shift, so 0, 1, 1, 4, 2, 16 is going to be off the grid, so I need to make sure I do not cross that vertical line for x equals 2. Draw this in and add my coordinates for my lattice points. And questions from today from anybody?